This is the last topic from chapter 16, and it's equilibria of slightly soluble salts. In the past, we called these insoluble ionic compounds, and as it turns out, everything has, I guess, some degree of solubility in water, even though it may be 1 in 10 billion. But it turns out that these formerly insoluble salts have a very, very small solubility in water, and they establish an equilibrium between the dissolved solvated ions and the solid form, which precipitates out of the water. And so that's what this unit is about. The equilibrium is established when the salt, which is kind of our nickname for ionic compounds. Wow, I don't know what I was writing there. Okay, I meant to write ionic compounds, reach their saturation point. So when the maximum amount of a particular ionic compound dissolves in water, there is set up a dynamic equilibrium. What we mean by dynamic is that just because one particle of an ionic compound dissolves, therefore separates into its ions and is solvated by water, it doesn't mean that particular particle will then forever remain dissolved. It's a back and forth process. So that particle a couple minutes later may recombine to form a solid particle of the salt, which resides outside of the water solution. And so it's back and forth, back and forth. But the bottom line is the concentration of the dissolved ion remains the same, even though the individual particles are going back and forth. The equilibrium constant, capital K, for this process is called Ksp. Sp stands for solubility product. This is just kind of a visual of the equilibrium process, showing you that while the concentration of dissolved particles in water remains constant, it is a dynamic process. Individual particles are going back and forth between the solid phase and the dissolved solvated phase. Remember what equilibrium means. It means that the rate of the forward process equals the rate of the reverse process. And that's why the concentration never changes, because the rate of dissolving and precipitation are equal to one another. There's something unique about writing the equilibrium expressions for Ksp processes, and that is that this really isn't a chemical reaction, but I'm going to call these reactants anyway. The reactant side for Ksp dissolving of a slightly soluble salt will always be a solid. Okay? For all practical purposes, these ionic compounds are really insoluble, so we put S for solid after them because there's such a trivial amount that dissolves. But because of that, and because of our rule that pure solids and liquids are not included in equilibrium expressions, you will never see the equilibrium expression for a slightly soluble salt containing a denominator. So remember that K values are always products, right, over reactants. So again, the reactant on all these cases is a solid. Solids are not included in the equilibrium expression. So just kind of make a note of that. It's the first very important concept to have, that Ksp expressions never have a denominator. I also want to point out to you that the typical Ksp values can get really, really tiny. Okay, so 10 to the minus 36, 10 to the minus 29. I've even seen some that are as small as 10 to the minus 70 something. So I didn't want you to start working Ksp problems and get these crazy small Ksp values and think that you had done something wrong. And the K values for Ksp, just like all other equilibrium values, have the same correlation. That is, the larger the Ksp value, the larger any K is, actually, that means the more product you have formed. And in this case, since we're talking about solubility, more product means more soluble. Okay, so if I were to tell you to look at this table and tell me what the most soluble ionic compound is shown in this table, what would you choose? Well, you would choose the one that has the largest Ksp value. And by glancing at that, I think that it may be calcium sulfate. That looks like that might be the largest value. Let's clarify exactly what we mean by solubility. A lot of students tend to mix up if a problem asks for the solubility product expression. It's talking about Ksp. If it simply asks for solubility or molar solubility, that is not Ksp. When something asks for molar solubility, they're just asking for the concentration of the salt or ionic compound in, and since it's molar, they're asking for units of moles per liter, which is molarity. Okay? So keep that in mind because some problems ask for molar solubility and others ask for the Ksp expression. They are different. There is a correlation between molar solubility and Ksp. Okay? As solubility goes up, Ksp also goes up. So there is a correlation, but they are different. Let's work out a simple sample problem. This is one of the most basic. This might be like a multiple choice on your test. If you're hearing that squeaky sound in the background, that is my dog chewing on a squeaky ball. So just thought I'd tell you. I hope it doesn't drive you crazy now. So copper bromide, which is a slightly soluble salt, has a solubility. It's not as small as a lot of the others, 2 times 10 to the minus 4 molar at 25 degrees Celsius. It says calculate its Ksp value. The first thing I want you to do, basically any equilibrium problem, is to write the equation that represents the equilibrium. And so I promise you in your test that I will give you the formulas for all this, even though you should know them. I'm not going to tax your brain in that way. I'm going to tax your brain for equilibria. So copper bromide, we're talking about Ksp. So that is it dissolving. Of course, all ionic compounds, when they dissolve, separate into the ions. Let's put the phases of matter just since it's Ksp. Okay, and so the ions are always aqueous, AQ. And of course, every slightly soluble salt is termed a solid. So there's our equilibrium expression. So you want to do that first, and then you want to write the expression for the Ksp. And that, remember, there is never a denominator because the reactant or the starting salt is insoluble, quote, in quotes. So here's the Ksp expression. Okay, and so now it involves an ice table, as almost all equilibria do. So on the next page, we're going to write out an ice table and plug in the values from the ice table in our Ksp expression. So here's our equilibrium expression. Of course, the initial solid salt is never going to be part of the equilibrium, so I'm just going to put a big X there. The amount we have dissolved starts as 0. They're both present in a 1-to-1 ratio, so they're both represented. That should be plus X, plus X. And so our Ksp expression in this case is really X squared. It turns out, however, that we know X. X will pretty much always be the solubility. Okay. And that was given to us. 2 times 10 to the minus 4. So we could have set up the ice table like this using X values, or instead of X values, we could have just immediately plugged in what we were given, realizing that that is in effect solubility. Okay, so now Ksp is simply, okay, X we know is 2 times 10 to the minus 4, and square that. And the Ksp value is 4 times 10 to the minus 8. So that one's pretty simple. Here's another one, and I'm going to guide you along a little bit. I've introduced another little twist in it, in that it's not a simple ionic compound where the cation and anion are present in a 1-to-1 ratio. Now we've got a little bit more complicated. So your first challenge, and I've guided you, I won't normally do this in problems, but I'm trying to kind of ramp or scaffold the difficulty for you in hopes that you'll follow me. So first you want to write an equilibrium expression for the dissolution of bismuth sulfide. If you can do that, go ahead and shut the video down. Try to do it yourself first because I'm going to write it out now. All right, so we get 2 bismuth cations. It's good to show charges. Having accurate charges is not going to alter or mess up your final answer for Ksp and solubility values, but it is important to represent the cation and anion with their appropriate charge. Kind of a quick little trick to remind you, you can do a reverse crisscross to get charges, so whatever the subscript is on this atom becomes the charge on the other one, and vice versa. So bismuth has a +3 charge, and we have 3 sulfurs, and they have a -2 charge. So that's the equilibrium expression, and the Ksp would then be concentration of bismuth squared times concentration of sulfide cubed. Okay, remember that the coefficients become exponents. Okay. All right, so you want to set up an ice table using the equilibrium expression, which I'll do on the next page. If by some chance at this early date you think you can do that on your own, go for it. That's the way you succeed, is solving problems on your own. One of the first things that you want to do is assign stoichiometric values. That's so important. Well, it's important in all equilibrium, but it's really the crux of a Ksp problem. So for every 1 bismuth sulfide we dissolve, we get 2 bismuth cations and 3 sulfide anions. So if we call the initial bismuth sulfide, since there's only one of them, X, then the amount of bismuth ion that's formed is going to be 2x, twice as much, and the amount of sulfide anion that's going to be formed is 3x. So that's what goes into the ice tables. Now you have to remember the Ksp expression. Listen really, really careful for the next couple minutes. So even re-listen to it if you need. This is it. This is the whole key, what I'm getting ready to do right now. So the Ksp expression we wrote on the previous page is this. Okay. Now we're getting ready to plug in these equilibrium values. Pay very close attention because you're going to feel like you accounted for the stoichiometry twice. So Ksp equals now, what is the concentration of the bismuth cation? It's 2x. Okay. Now, we still have this square here. So you are going to feel like you accounted for the 2 bismuth cations 2 times because you doubled the concentration and you squared it. That's what you're supposed to do, okay? The same thing. Sulfide concentration is represented by 3x, and you still maintain the cube. That gets kind of complicated, doesn't it? Okay, so now go back and reread the question, the original question. Solubility. Remember I told you that that's x, okay? So now you can plug those values in, and you don't even have to show x's in your ice tables. If you'd rather, just from the get-go, instead of, for example, putting 2x, you would put 2 times 1 times 10 to the minus 15, okay, from this. If you want to do that directly in your ice table, that's perfectly fine. So once you plug in the values and you solve it, check this out. Look at this Ksp value, 1.1 times 10 to the minus 73. So I would say bismuth sulfide, not very soluble in water, okay? But again, notice you can, in fact, get values that are this small for Ksp. You try this one completely on your own, even if you feel like you have no idea what's going on. Put the video on pause, go back to the problems I just worked out, whatever you need to do, but you make yourself try something on your own so that you can kind of self-assess where you're at. All right, so I've set up the skeleton for the ice table, and instead of using X values, because the problem did in fact give me the molar solubility, I'm going to go ahead and just use those values in the ice table. So I'm going to pay very close attention to the stoichiometry. So for every one of the PbBr2 I dissolve, I make 1 lead ion and I make 2 bromide ions. Okay, so if I call this initial solid material X, I'm going to form X concentration of the lead ion and 2X concentration of the bromide. So there are my X values, but I'm going to actually use numerical values in the ice table. I'm going to start out initial as always for Ksp. Well, not as always. You'll see farther down the line. But if I'm going to call them 0 for now. And I am forming X amount of the lead as it dissolves. And that's the solubility, which was actually given in the problem if you need to go back and read the question. But it was 2.17 times 10 to the minus 3. And the bromide formed is twice that much. So see if I can do math in my head. So that would be plus 4.34 times 10 to the minus 3. Okay, and so my equilibrium concentration of the lead ion is simply 2.17 times 10 to the minus 3, and the equilibrium concentration of the bromide ion. All right. So now I'm just going to plug these equilibrium values into my expression for Ksp, which I don't think I wrote yet. So concentration of lead times concentration of bromide raised to the 2 squared. Plugging in the values that I got here. See, concentration of lead is 2.17 times 10 to the minus 3. Concentration of the bromide is 4.34 times 10 to the minus 3. Do not forget the square. Okay, now I'm just going to do this math and see what my answer is. So when I do that calculation, I get 4.09 times 10 to the minus 8 for my Ksp value. So if you go back to the choices, I think that was answer choice C on the original question in the previous slide. Now if you read this sample question, it's a little bit different. It's kind of working in the reverse direction. So in the first 2 questions, they gave us molar solubility, and we were asked to solve for Ksp. This is a type of question where they give you Ksp, and you're asked to solve for molar solubility, which is X, remember? Something that'll have molarity. All right, so here's a simple one. As always, and again, I promise I'll give you the formulas on the test. Here's the formula for zinc hydroxide. Zinc always has a charge of +2, by the way, just kind of prompting your prior knowledge. Hydroxide has a charge of -1, so we need 2 hydroxides to balance the charge so that the net charge is 0. Anyway, so here's the dissociation equilibrium for zinc hydroxide in water, and the equilibrium says always make 1 zinc cation, and we make 2 hydroxides, so it's X and 2X as normal. So in this case, we are not given X, or the molar solubility, in the question itself, so we have to keep them in the X format. Write the expression for Ksp. Don't forget your square, okay, because there are 2 hydroxides. And plug in your values. Equilibrium concentration for zinc is X, and that for hydroxide is 2X. Again, don't forget the square. Again, you're going to feel like you're compensating for that 2 hydroxide 2 times because you've doubled the concentration and you've also squared it, but that's what you do. Now, again, if you've been kind of drifting off board, tune in. This is very critical, very common place to make an error. What is 2x squared? Okay, it is 4x squared. Okay, well, 2x in parentheses squared is 4x squared. I can't tell you the number of students who say that 2x squared in parentheses is just 2x squared. They forget to square the 2 inside the parentheses. Okay, so be aware of that, please. So when you multiply 2x in parentheses squared times x, you get 4x cubed. That is by far the most common KSP expression you will come across, 4x cubed. Okay, so just remember that. If you are working a problem out and you end up with something like 2x cubed, I guarantee you forgot to square your 2. So anyway, so then how do you simplify? If you get 4x cubed equals some number, how do you simplify that? The first thing you do before anything else is divide both sides by 4. Okay, get rid of that 4 before you take the cube root. That's also another common error. So what I would recommend right this minute is that you pull out your calculator and try to solve for x. Let me pull this up here. Try to solve for x and make sure you get the same value, okay? Because I'd hate for you on a test to work through this complicated ICE table and then not be able to do the algebra and solving for x. So take a minute, make sure you know how to do that. Here's another sample problem that is asking you, again, to solve for molar solubility, x instead of KSP. And on a test, I won't give you these steps, 1, 2, 3. Again, I'm trying to scaffold it for you. If you think you can do it, give it a try, okay? And then I'll work through it right now then. The steps that I've given you here are the basic steps that you will always do for a KSP problem. So write the dissociation equation. You got to watch out for polyatomic ions if you're not comfortable with working with them or if it's been a while. So recognize that PO4 is a polyatomic. Don't try separating it into individual ions, or individual atoms, I mean. And so, hear my dog drinking water in the background? Okay, so anyway, here is the equilibrium expression. Complete an ICE table. So as always, put an X under the solid. That's not going to affect your equilibrium constant. And pay attention to your stoichiometry. For every one of these we dissolve, we make 1 aluminum cation and 1 phosphate. So that makes everything easy. I'm going to be lazy. Straight put in my equilibrium values of aluminum and phosphate ions. They're just X. I was given the KSP value, so I'm going to write the KSP expression. This is a pretty straightforward one. Okay, and put in my X values. I don't know solubility. Okay, so in this case, KSP simply equals X squared. Okay, and we know that KSP is the value of it. It was given in the problem. So now we have 9.83 times 10 to the minus 2 equals X squared. So what do you do to solve for that? You simply take the square root of both sides. So X would equal the square root of 9.83 times 10 to the minus 20. I think I forgot to write the 1 there. And so it would equal here's a problem for you to do completely on your own. The quiz is available, I believe, for review in Learning Catalytics, but it is not activated now. It was given during class, so if you weren't in class, then you don't have access to it. And so see if you can do this one on your own, and I will work it for you on the next page. Actually, I think I have enough room to work it out right here. Okay, I'm going to go through the steps that I always recommend, and that's to write out the equilibrium expression. paying attention to stoichiometry, and write out the Ksp expression. I'm going to write up here so I don't mess up my ice table. Ksp, concentration of calcium, times concentration of fluoride squared. Okay, and we are given that value. And we're asked to calculate molar solubility, which remember is simply X. Okay, here we go. We make twice as much fluoride as calcium, so we're going to call that plus 2X. And there are our values. And now I need to go to the next page to plug these equilibrium values into the Ksp expression. Alrighty, so concentration of calcium was represented by X. That of fluoride is represented by 2X. Don't forget to also square the fluoride. Now remember what I said about 2X in parentheses squared. So if you do your algebra correctly here, this Ksp value is equal to X times 4X squared, or 4X cubed. Okay. To simplify and solve for X, the first thing you want to do is divide both sides by 4. Okay, so it made the math easy here. That means that 1 times 10 to the minus 11 equals X cubed. And that means that X is the cube root of 1 times 10 to the minus 11. Okay, cube root, and I think most of you probably know this, so is the same thing, just to make it easier in your calculator if you don't have a cube root function, as that number raised to the 1/3. So when you solve that, you get that the answer is, and I'm running out of room, let's see, 2.15 times 10 to the minus 4. And this is X we solve for, so what is X? It is solubility, and the units are molarity, so don't forget your units. Okay, so what that tells us is if we put a glob of calcium fluoride in water, that this is the concentration of it that will dissolve in that water. And once it reaches this concentration, it's maxed out at solubility, and no more will dissolve. That's the end of the discussion on Ksp and the end of Chapter 16.